Hello. In today's video we're going to be looking at chapter 16, which is the acid-base equilibrium chapter. In this particular video we're going to be looking this pre-lecture video, we're going to be touching on our different definitions of acids and bases, conjugate acid-base pairs, relative strengths of acids and bases based on the structure of their conjugates. We're going to look at the autoionization of water. We're going to look at pH and pOH of strong acids and strong bases, relating them to hydronium and hydroxide concentration, or vice versa. And then we're going to look at acid strength, base strength, and lastly we're going to look at weak acids and weak bases in difference to strong acids and strong bases, and looking at their equilibrium constants. Okay, so first we're going to look at our definitions of acids and bases. So we have a couple different ways of defining acids and bases. Our first one are Arrhenius acids and Arrhenius bases. So the definition was determined by Savante or Arrhenius. So Arrhenius acids are defined as a substance that gives off H plus in water, or a substance that increases the hydronium or H plus concentration in water. The base is going to be something that increases the hydroxide concentration in water. Okay. Next is our Bronsted-Lowry acid and base. The acids are a substance that donate a proton. H plus. And then a base accepts a proton. And then our last definition is Lewis acid and Lewis base. So our Lewis acids are substances that accept electron pairs. And then the base is a substance that donates a pair of electrons. So with each of these definitions I'm going to go more in detail in a further video along with in class, but I'm going to look particularly at Bronsted today. It's one of the most common definitions, so we're going to look at Bronsted-Lowry acids and bases. So as I said, it's a substance that donates a proton if we're talking about an acid, or accepts a proton if we're talking about base. So let's look at the idea of a proton first. So first, if we have a H atom, it's going to be a substance that has one proton, one electron, and 0 neutrons. Okay. So if we have a neutral hydrogen atom. But if we have a cation, so a substance that has a plus charge, we just have one proton. We have lost an electron, which is why we call an H plus ion a proton. Another thing we're going to look at is what happens to that proton in water. So protons are going to be unstable in water by themselves. So we never see them as individual ions. They're actually going to attach to any water molecules close by. And it's going to form hydronium. So H plus water will produce hydronium. Okay, and that's how our acid, when it dissociates to produce H plus ions, and that's what an acid does, it dissociates to produce H plus ions. When that occurs, that H plus ion is going to attach to a water molecule. So we can kind of use the idea of H plus or H3O plus simultaneously, or they're basically synonymous. So we can use them interchangeably. So anytime, or specifically in aqueous solutions. So if we have an acid dissociating, producing H plus ions or protons, they are going to then attach to a water molecule to produce hydronium. Okay, so a little bit more about Bronsted-Lowry acids and bases. If we have, I'm actually going to go to a different color real quick. If we have an acid, such as HCl, it can react with water and produce hydronium. So this hydrogen is donated from hydrochloric acid and accepted by the water to produce hydronium. So this donates a proton. So this is our acid. This accepts a proton. So this is our base. Okay. And when we have an acid that loses a proton, to produce a substance that has one fewer proton, this is called a conjugate acid-base pair. So a conjugate acid-base pair is going to be a set of two substances whose chemical formula differ by the presence of a proton. So HCl, Cl minus would be a conjugate acid-base pair, and also H2O and H3O plus are a conjugate acid-base pair. And we call it a conjugate acid-base pair because one of the substances is an acid, one of it is a base. In the case of HCl, HCl is the acid, and then Cl minus is a conjugate base. In the case of water and hydronium, water is a base, and then hydronium is a conjugate acid. So the things on the left side of our reaction will always be the acid and the base. The things on the right side will be the conjugate acid and the conjugate base. And it will only differ, the substances will only differ by 1 proton. Okay. Next topic I want to talk about is the acid-base properties of water. So when we have a batch of water, we have a bunch of water hanging out together, if we have 2 molecules of water that collide with each other with enough energy, they will have a transfer of a proton from one of those water molecules to the other water molecule. So they will react with each other. This pair of electrons right here will come in and form a bond with this hydrogen, and then we'll break that bond between that oxygen on the right and hydrogen. And what we produce is hydronium and hydroxide. Like so. Now, this is an equilibrium process. And anytime we have an aqueous solution, there will always be some amount of hydronium and hydroxide, or just pure water will have some amount of hydronium and hydroxide. So the idea that a water molecule can act as either a acid or a base, it can either donate or accept a proton, we call this amphiprotic. So it acts as either a acid or base. Okay, and in the case of the autoionization of water, which is what this is, water is acting as both an acid and a base. So this equilibrium that occurs in water gives us what we call our equilibrium constant of our water, or ion product constant of water, Kw. Where our Kw is equal to our hydronium concentration times by our hydroxide concentration. On the bottom of that would be water, but water would be 1 in this case, so it would just be that. And this Kw is 1.0 times 10 to the negative 14 at 25 degrees Celsius. So that equilibrium constant can change at different temperatures, but at 25 degrees Celsius, the product of the multiplication of the hydronium concentration times the hydroxide concentration will always be 1.0 times 10 to the negative 14 in any aqueous solution. Regardless if we have an acidic solution, a basic solution, or a neutral solution. So if we have a pure water solution, our hydronium concentration and our hydroxide concentration will be equal to each other, so they are both equal to 1.0 times 10 to the negative 7. But as we get an acidic solution, our hydronium concentration will go up versus our hydroxide concentration, and then a basic solution, hydroxide concentration will go up in comparison to our hydronium concentration. Okay, so pH and pOH measure the acidity and basicity of a solution. So we have some ways of calculating this. So our pH is equal to our negative log hydronium concentration, and then pOH is a negative log of our hydroxide concentration. And in this case, the lower the number, the greater the concentration of whatever substance. So if we're looking at pH, if we have a really low pH, it means we have a very high hydronium concentration. Okay, and our pH scale generally goes from 0 to 14, although if you have a very acidic thing, it'll be negative. Okay. Some other calculations you're going to need to know is pH plus pOH is equal to 14. Okay. And we're going to look at both strong acids, strong bases, weak acids, and weak bases. So, with strong acids, generally, I'm going to give you guys a list of the strong acids, but strong acids and strong bases are going to be substances that completely dissociate in water. Okay, so they're going to completely break down. We call these electrolytes, specifically strong electrolytes. So they're going to behave just like my ionic compound does. Weak acids and weak bases do not completely dissociate. They are going to partially dissociate. So these are considered weak electrolytes. And these are going to have Kas and Kbs associated with them. So our Ka is our acid dissociation constant. And our Kb is our base dissociation constant. So again, I'll go over a list of our strong acids, our strong bases, and then anything that's not a strong acid or a strong base will be considered a weak acid or a weak base. Okay, so just as a note, kind of relating strengths of acids and bases. Strong acids will have weak conjugate bases. Strong bases will have weak conjugate acids. And then with our weak acid and our weak base, we form weak conjugates. And these are very weak if we have a strong. Almost to the point that the conjugates are neutral, so they'd have a neutral pH. Our weak acids will have weak conjugate bases, but the weaker the acid, the stronger, though not strong, not classified as strong, the conjugate base. So what I mean by this is a weak acid will have a weak conjugate base, but if we're kind of comparing, if we have a weaker acid, it'll form a less weak conjugate base. A stronger weak acid or a less weak acid will produce a weaker weak conjugate base. So they'll still form, like if we do kind of take strong acid and then a weak acid, and we're going to put strong but weaker. Okay, so we can classify strong acids as really strong or strong, weak acids as stronger or weaker. And then we have very weak, basically neutral. A strong acid will give a very weak base. A strong but weaker we'll do this. Still a very weak. And then a weak acid will give a weak base that is weaker. A weaker weak base will give a weak base that is stronger. So they're kind of, the conjugates will be the inverse of the starting material. Just a strong will go to very weak, but a weak will stay weak whether it's a acid or its conjugate. Okay, Last thing I want to look at is Ka and Kb, and then some. Yeah, that's really so. Ka and Kb. So Ka, if we have a weak acid, it reacts with water. It's an equilibrium process producing hydronium and hydroxide, or sorry, hydronium and our anion. Our Ka would be given by our hydronium concentration times by our anion concentration divided by our Ha. And for a weak acid, our Ka is going to be less than 1. Okay? If we have a base, we're talking about a Kb. So our base will react with water to produce hydroxide ions and cation. And our Kb will be equal to our hydroxide concentration times by our cation, our conjugate acid, if you will, divided by our base concentration. Another way you can look at a base is a anion. So an anion will react with water to produce Ha plus hydroxide. So our Kb could also look like this. Our Ha concentration times by our hydroxide concentration over our A minus concentration. Okay? So a weak base will also have a Kb that is less than 1. If we have a strong acid, or strong base, we can very easily calculate our pH or pOH. So with a strong acid, it completely dissociates with a one-way arrow to produce hydronium plus our A minus. So whatever our starting concentration is, we're going to call it CHA. We're going to subtract that and add that here. And we will get that concentration over here. So our concentration of our strong acid will break down to produce our hydronium and our A minus. So we can just say pH is equal to negative log H3O plus, which will be equal to our concentration of our weak or our strong acid. For a base, we have some sort of metal. It'll be a alkali metal or alkaline earth metal, and it will not actually react with water, it'll just completely dissociate. Like so. So whatever our starting concentration is of our base, When it dissociates, it will dissociate completely. But here we have to take into account stoichiometry because we can have multiple hydroxides. So we'll just multiply our N value, which is equal to the charge on our cation. So in the case of something like calcium hydroxide, our N is 2. Sodium hydroxide, our N is 1. Okay, so we can very easily solve for our POH by taking our negative log of N times by our initial concentration of our metal. If we have a weak acid or weak base, we cannot directly calculate our pH because now we are talking about something that's in equilibrium, so we'll need to use an ice table. To solve for X. Okay, that's everything for this pre-lecture. I'll see you guys later.